We're in section 8-1, and we're doing series approximations of differential equations. So first thing we're going to look at is we may remember something called a Taylor expansion. And we're going to do it about 0 to make it easy to write. And the Taylor expansion says that any function, doesn't matter what it is, I can turn it into a expansion, a series expansion. F of x will be f prime f0 at divided by 0 factorial, which is 1, plus f prime of 0 divided by 1 factorial f double prime at 0 divided by 2 factorial plus out to f n prime 0 factorial divided by n factorial, blah blah blah, out to infinity, forever and ever. And every function has a Taylor expansion. Every differential equation has, well, every differential equation that has an answer is a function that could be a Taylor expansion. So that's just one of those things that you think about. And so you use Taylor expansion, and we're going to look at sine x. There's my function, and we find f of x is sine x, and f at 0 is 0. And we look at f prime x, and we see that that's cosine x. And we see that y prime at 0 is 1. And then we look at f double prime of x, and we see that that's minus sine x. And f double prime at 0 is 0. And then we look at f triple prime x, and that's minus cosine x. And f triple prime at 0 is minus 1. So we see that the first few terms of the Taylor expansion for sine x are going to be x minus x cubed divided by 3 factorial, and we can continue that for a long time. So we'll just continue it for a long time. Plus or minus 1 raised to the n, x to the 2n plus 1 divided by 2n plus 1 factorial, and then out to infinity. Okay, well, so there does exist, if we have an answer, then it does exist. Well, if that's the case, then we can say, well, f of x, we'll start with f of x, and that's going to be summation n equals 0 to infinity, a n x to the n. And so the Taylor expansion is just powers of x with some coefficient. I just don't know the coefficient yet. And f prime is going to be summation n is equal to 1 to infinity, n a n x to the n minus 1. And the second derivative is going to be summation n equal 2 to infinity, n minus 1, n a n x to the n minus 2. And the third derivative of the function is going to be summation n equal 3 to infinity, n minus 2, n minus 1, n a n x to the n minus 3, and so on for as many of those things that we need. And so keeping that in mind, we're going to move on and say, well, yeah, but if I have a series expansion, well, we'll look at a function. Y prime minus y is 0. This has a characteristic equation, and the characteristic equation is r minus 1 equals 0, r is equal to 1, y of x is equal to e to the x, c1 e to the x. Well, clearly we wouldn't use this particular method on a problem like that because that's way too easy, so we're not going to do that. Now we have to worry about series expansions being diverging or converging. So if I take something that's 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, I keep on going that way, I find that this guy converges, and it converges to 2. But if I take something that's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and 1/6, 1/7, 1/8, if I take that guy, I find that he diverges. That I've got a 1 here, and I add it to another 1 that is there, and I take the next 5 guys and I get another thing bigger than 1, and I take another 7 guys and I get something bigger than 1, and I end up adding 1s, and I diverge, I go to infinity. So we have a rule, and it's a radius rule, because we want to know the radius of expansion. Now, for the purpose of this class, I'm never going to have you calculate these things, but if we have a function summation, we have a series summation 0 to infinity a n x to the n, and we look at rho, which is the limit as n goes to infinity of the absolute value a n divided by a n plus 1. And we find 3 possibilities. If rho is 0, then the series diverges. And B, if 0 is less than rho is less than infinity, then I converge if x, the absolute value of x is less than rho. And the other possibility, C, if rho is infinity. Now, how can rho equal infinity? Anybody got that figured out yet? I think the author is probably doing something weird here. If that case, then the series converges. Okay, well, so much for that theory. We're going to look at a problem. Going to look at number 2. Now, the math I'm doing you've probably never seen before, so pay attention. And on the next test, you get to do it many times. So there's our problem. Now, on the side here, we can say, well, this guy has a characteristic equation. R minus 4 equals 0. Y of x is going to be C1 e to the 4x. So when I get done, I probably will see something like that. In the meantime, what I have is y prime. So that's summation n equal 1 to infinity a n x to the n minus 1 n a n x minus 4. Summation n equals 0 to infinity a n x to the n is equal to 0. So what I'm going to do is I'm going to get my exponents of x to be the same. So I'm going to do a substitution in this guy, and so I'm going to let n equal n minus 1. And when I do that, I got summation n is equal to 0, because I put n minus 1 here. N becomes n minus 1. No, I want n plus 1. Yeah, that's better, n plus 1. I put n plus 1 here. The 1 goes over there, makes it a 0. Infinity. N plus 1. A n plus 1 x to the n minus summation n equal to 0 to infinity 4 a n x to the n is equal to 0. Okay, now I have the summation going 0 to infinity in both cases, so I can write it summation n equals 0 to infinity. I have n plus 1, a n plus 1 minus 4 a n x to the n is equal to 0. Now, we have an issue here, and it's called linear dependence. So I've got 1, and I've got x, and I have x squared, and I have x cubed, and I have x to the 4th. Are these guys linearly independent of each other? And the answer is yes, they are. So if they're linearly independent of each other, that means each of them individually has to be 0 for the summation to be 0. Okay, you want me to say that again, or you just listen to the video? So that being the case, I don't need the summation sign anymore. I can say that n plus 1 a n plus 1 minus 4 a n has to be 0, because each of these coefficients has to be 0. Those functions are linearly independent. Okay, I do that. I'm now going to rearrange this guy. A n plus 1 is equal to 4 a n divided by n plus 1. I'm going to call that my recurring formula. All right, now I got a recurring formula that has to continue. What is A0? I don't know. Why don't I know? Well, I don't have an initial condition. No initial condition means how can I know what A0 is? So I don't know what A0 is. So A0 is just going to be arbitrary. Okay, so A0 is going to be arbitrary. I don't know what it is. I'm then going to look at n is equal to 0. At n is equal to 0, I got A1 is equal to 4 A0 divided by 1. And then I look at n is equal to 1. I'm going to end up with an A2 is equal to 4 A1 divided by 2. And I look at that and I say, well, A1 is 4A0 divided by 1, so I've got 8. That was cool. 16 A0 divided by 2, which is going to be 8 A0. Okay, and then I look at n is equal to 3, and I've got A3 is equal to 4 A2 divided by 3, which is going to be 4 times 32. 32 A0 divided by 3. All right. And then I'll look at one more and go up to A4 and say n is equal to, this is equal to 2. N is equal to 3, and I get A4, and I get 4 A3 divided by 4, which is 32 times 16 divided by the 4 that's there. Okay, so that's going to be another 32 A0 divided by 3. Okay, so now I've got the first 1, 2, 3, 4, 5 terms. And normally that's what I ask you for, is the first 5 coefficients. So my final answer, y of x, is going to be A0 plus 4 A0x plus 8 A0x squared plus 32 over 3x cubed plus 32 over 3x to the fourth. And I'm going to check my work. So I'm going to go and say y prime of x is equal to 4a0, that's a plus sign, plus 16a0x plus 32a cubed, a squared plus 128 over 3x cubed. Okay, when I get done, I want to have 0. No, I don't. I want to have e to the 4x. When I get done, I want to have e to the 4x, I think. No, I want to have 0. Okay, when I get done, I want to have 0. Okay, I want minus 4 of them and one of these guys. And so that term goes away, this term goes away. 4 times 8, that term goes away. Minus 4, this term goes away. I can't check that term because I'd have to have the x to the fifth term, but it looks like it's going to work. So 0 is equal to 0, check. And then I say, well, what is the expansion of e to the x? Well, e to the x is 1 plus x squared over 2 factorial, which I don't have to write the factorial for, x cubed over 3 factorial. What is e to the 4x? That's going to be 1 plus 4x plus 16 over 2, 8x squared, plus 4 to the third, 16 times 4, divided by a 2, 32 over 3x squared. And we said that it was going to have a constant in front of it, so it's going to have C1 in front of it like that. Well, that's my A0. My A0 is sitting there, even though I didn't put one here. A0, A0. Did I leave them out at those other two places too? Oh, bad. A0. Okay, so it worked. It solved that problem. It got the answer that we wanted. Isn't that lovely? Just a matter of keeping track of what one's doing. Okay, number 4. Y prime plus 2xy is equal to 0. Okay, so I've got summation n equal 1 to infinity n a n x to the n minus 1 plus 2x summation n equals 0 to infinity a n x to the n is equal to 0. Okay, now we'll do a substitution into this guy. Well, we won't do the substitution quite yet. We'll go and bring in the x term coming this way. All right, so I got summation n equal 1 to infinity n a n x to the n minus 1 plus summation n equals 0 to infinity 2 a n x to the n plus 1 is equal to 0. Okay, so I want to get the exponents to be the same, and I want to do as least work as possible, so I'm going to go summation, I'm going to do a substitute. N is equal to n plus 2. Okay, because if I put an n plus 2 for that n, I'll end up with an n plus 1 and get the same as I have over there. Okay, so that should be nice. Summation n is equal to minus 1 to infinity n plus 2, a n plus 2, x to the n plus 1, plus summation n equals 0 to infinity, 2a n x to the n plus 1 is equal to 0. And then I say, well, I go 0 to infinity here, minus 1 to infinity there. That's inconvenient. So I'm going to remove the n minus 1 term, and n equal to minus 1 term from that summation. Okay, so that's what I'm going to do. And so I'm going to have n is minus 1. So this becomes a 1. N is minus 1. So I have a n x to the 0 plus summation n equal to 0 to infinity. I have n plus 1, a n plus 1, x to the n plus 1. Oh, yeah. I removed this guy, so he's out. This is still a 2, that's still a 2, that's still a 1. Okay, plus, now I got the same 0 to infinity indexing, so I can throw this guy in, 2a n x to the n plus 1 is equal to 0. And the summation goes over the whole thing. Okay, so that being the case, all the x to the n's have to be linearly independent. So a n x to the 0 has to be 0, which implies what? Which implies a, it's not a n though, it's a minus 1. A minus 1, which implies a minus 1 has to be 0. Okay, and then I look at what's inside the brackets and I get a recurring formula, and it says a n plus 2 is equal to minus 2a n divided by n plus 2. Back up to here. When I take out n minus 1, that becomes a 1, this becomes a 1. So it's not minus 1 that's 0, it's a 1 that is 0. Okay, so a1 is 0. Okay, so there's my recurring formula. And where do I start? This is for all n greater than or equal to 0, because I start at 0. Okay, so what is a0? a0 is arbitrary, as it's always been, as it always will be, unless it isn't. We're going to start at a equals 0. So at a equals 0, I have a2. a2 is equal to minus 2 a0 divided by 2, also known as minus a0. a3 is equal to minus 2 at n is equal to 1. At n is equal to 1, a3 is going to equal minus 2a1 divided by 3, which is 0, because a1 is 0. At n is equal to 2, I have a4, and a4 is going to be minus 2 a2 divided by 4, and a2 is minus a0, so this is going to be 1/2 a0. Okay, and then at n is equal to 3, I have a5, which is going to be 0. And then at n is equal to 4, I'm going to have a6, which is going to be minus 2a4, which is 1/2 over a0 divided by 3 factorial 6 divided by 6. And we're going to call it minus a0 over 3 factorial. Well, yeah, we'll call it 3 factorial. We don't like to call things 6 when we can call them 3 factorial. Okay, so I got an answer, final answer. Y of x is equal to a0 minus a0x squared plus a0 over 2 x to the 4th minus a0 x6 over 3 factorial. Okay, so that's my final answer. And I'm going to check my work, because in these particular problems, how do you possibly know that that's right unless you check your work? So I got 2x times y, which is going to be a0 minus a0x squared plus a0 over 2x to the 4th minus a0x to the 6th over 3 factorial. Y is going to be, and I want 1 of y, going to be, that guy goes away, minus a0x plus a 2a0x cubed minus a0x to the 5th. Okay, so does that look right? Yeah, that probably looks right. Okay, so, and going back to the original problem, I want one of the derivatives and 2x of the other guy. Okay, so I got the right guys. Okay, so I've got 2x a0. Why don't I have 2x a0 here? Well, because I took the derivative wrong. That's a prime. Hope I did the other ones right. So those two guys go away. I got 2x cubed minus 2x cubed a0 and 2x cubed 0. I've got x to the 5th, a0x to the 5th, a0x to the 5th. So I'm supposed to have 0. I have 0. I have something hanging out there, but in order to get rid of it, I'd have to get the other term. So it looks like I got the problem right. So that's the cool part. All right, now we're going to do number 10. Okay, we're going to be working on problem number 10. 2x minus 1, y prime minus 3y is equal to 0. Okay, so I'm going to do 2x summation n equal 1 to infinity n a n x to the n minus 1 minus 2 summation n equal 1 to infinity. See, when I have two terms, so I'm going to break them up. This makes it easier that way. N a n x to the n minus 1 minus 3 summation n equals 0 to infinity a n x to the n is equal to 0. Okay, I'm going to bring the stuff inside the summation sign. Summation n equal 1 to infinity 2 n a n x to the n minus summation n equal 1 to infinity 2 n a n x to the n minus 1 minus summation n equals 0 to infinity a n x to the n is equal to 0. Okay, well, I have x to the n, x to the n, x to the n minus 1. So I'm going to do a substitution, and I'm going to say n is equal to n plus 1 for the middle summation sign. And I'm going to get summation n equal 1 to infinity 2n a n x to the n minus summation n equals 0 to infinity 2 n plus 1 a n plus 1 x to the n minus summation n equals 0 to infinity a n x to the n is equal to 0. Okay, and then I'm going to remove M-O-L-E-R-E. I misspelled remove. Okay, I'm going to remove n equals 0 from both of these guys, so my summations will be indexed at n is equal to 1. Okay, so I got n equals 0. So I've got minus 2 a0 minus 2a0, and moving back I see I have a 3 here that I left out, and I have a 3 there that I left out. Okay, so where was I? Minus 2a0 minus 3 minus 2a1 minus 2a1. When I take the 0 guy out, it makes it a1 minus 3a0 x to the 0 plus summation n equal 1 to infinity. We're going to put everybody in here now. 2n a n minus 2 n plus 1 a n plus 1 minus 3 a n x to the n is equal to 0. Okay, now again the terms have to be linearly independent, so the x to the 0 term coefficient has to be 0. So 2a minus 2a1 minus 3a0 has to be 0. a0 is arbitrary. Which means a1 is going to be, the minus sign goes over there, makes it positive. This minus sign makes it negative. Minus 3a0 over 2. Minus 3a0 over 2. I have a recurring formula that's coming from this. It says a(n plus 1 is going to be minus 2 n a n minus 3 a plus 3 a n divided by minus 2 n plus 1. Okay, and I'll work some algebra on that and say a n plus 1 is equal to 2n minus 3 a n divided by 2n plus 1. And that's going to be for all n greater than or equal to 1. Okay. I think I'm all right to that point. So a0 is arbitrary. a1 minus 3a0 over 2. Doesn't look too much like a 3 though. Minus 3a0 over 2. A to the n plus 1. Okay, so for n is equal to 1, I'm looking at a2 equal to, that's a minus 1 times minus 3 over 2 a0 This is a 1, 2 and 2 is 4, so I have 8a0 over, no I don't. So I have 3a0 over 8. Okay, for n is equal to 2, I have a3, and so 2's in there, that's a 4, minus 3 is a 1, so I'm going to have a2, which is 3a0 over 8, divided by 2 times 3, which is 6. So I'm going to have a0 over 16. At n is equal to 4, I have n is equal to 4. N is equal to 3. I have a4. A4. I put a 3 in here, that's 6. That gives me 3 here, that's a 6 minus 3 is going to give me a 3. A3, which is 9, which is a0 over 16, divided by, I put a 3 here, that's 4 times 2, that's 8, and I've got 3a0 divided by 124. Okay, so putting it together, y of x is equal to a0, which is arbitrary. A1 is minus 3a0 divided by 2x. And a2 is 3 over 8 a0x squared plus a0 divided by 16x cubed plus 3a0 over 124x to the 4th, and that checks with backup book. So we're moving on. All right. So we're going to redo problem number 2. Okay, so I'm going to do it a little bit different. So we're going to redo. And number 2 was a homogeneous problem, so we're going to make it non-homogeneous. Y prime minus 4y, and we're going to say it's equal to sine x. So I'm changing problem number 2. It's not equal to 0, it's equal to sine x. And so, what do we got? We've got, what is sine x? Sine x. Well, the series expansion for sine, summation n equals 0 to infinity, minus 1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. Isn't that lovely? So my equation becomes summation n equals 1 to infinity, an x to the n minus 1 minus 4 summation n equals 0 to infinity an x to the n minus summation n equals 0 to infinity minus 1 to the n x to the 2n plus 1 divided by 2n plus 1 factorial is equal to 0. Isn't that wonderful? Don't you just love it? Yes, I just do. That's just wonderful. Okay, so what do we have? Well, we're going to do a substitution into this guy. N is equal to n plus 1, so we get all of our indexing the same. And we'll have summation n equals 0 to infinity, n plus 1, a n plus 1, x to the n, minus summation n equals 0 to infinity for a n x to the n minus summation n is equal to 0 to infinity minus 1 x to the 2n plus 1 over 2n plus 1 factorial is equal to 0. Okay, so this is where we look at this and say, well, what I need is two recurring formulas. I need a recurring formula when n is even, and I need a recurring formula when n is odd. Okay, so if I look at when n is even, then the sine function is 0 for n even. Sine is 0. So the sine function goes away, and my recurring formula becomes a n plus 1 is equal to 4 a n divided by n plus 1. And when n is odd, I have a recurring formula that says a n plus 1 is equal to 4 a n divided by n plus 1. And it's going to, because the sine function goes plus then minus, then plus then minus, then this guy is going to have to go plus then minus 1 over n plus 1 factorial. So I have two recurring formulas. One recurring formula for when n is even, one recurring formula for when n is odd. And now you have to convince yourself that that's going to work. Okay, well, what is A0? A0 is arbitrary. I think I need a dime every time I say that. A0 is arbitrary. At n is equal to 0, we're going to have A1. And A1 is n equals 0 even or odd? Yes, that's a good question. Well, in this case it's even, and I'm going to have 4A0. And then I'm going to look at n is equal to 1, which is clearly odd. A2 is equal to 4A1 over 2 plus 1 over 2 factorial, which becomes 8A0 plus 1 half. Okay, when n is equal to 2, I have A3, which is going to be even, which is going to be 4 over 3, A2, which is 4 over 3, A8, A0 plus a half, which is 32, A0 plus 2 over 3. Okay, now we're looking at n is equal to 3, which is odd, and n is equal to 3, and I'm looking at A4. Okay, so A4 is going to be 4 A3 over 4 minus 1 over 4 factorial. Okay, it's because it was plus the first time I used it, plus 1 over 2 factorial. It has to be negative the second time I use it. Okay, so that's going to be 4 times 32a0 plus 2 over 3 minus 1 over 4 factorial, back to the recurring formula. Let's see. Minus 4 is minus 4 over 4 factorial. Okay, so the 4 factorial goes on the bottom, I think. No, the recurring formula has to have this on the bottom. Did I put it on the bottom on the first one? Yes, I did. Yes, I did. I put it on the bottom of the first one. I put parentheses around the whole thing. Okay, so that's good. And where was I? Divided by 4. All right, so A4 is going to be 32A0 plus 2 divided by 3 minus 3, 1 over 3 factorial. Okay, the 4 goes away, the 4 goes there, makes it a 3 factorial. Okay, so that being the case, we can write down a final answer, assuming we can see all those things. Y of x is equal to A0 x plus 4 A0, just A0x, A0 plus 4 A0x plus 8 A0 plus 1/2 x squared plus 32 A0 plus 2 over 3 x to the third plus, I need more room, give me more room, plus 32 A0 plus 2 over 3 minus 1 over 3 factorial x to the fourth. Okay, so I got all that. Y prime is going to be 4A0 plus 16A0 plus 1 x plus 32A0 plus 2 x squared plus, do I have enough room? 1, 2, 8, A0, I don't have enough room. Okay, so we'll move down a little bit. Plus 1, 2, 8 A0 plus 8 over 3 minus 4 over 3 factorial x cubed. Okay, so now we're going to add those guys together, and what I want to see is I want to see an x minus x cubed over 3 factorial, which are the first two things of sine, first two terms of the sine guy. Okay, and what was the problem we're working on? It is y double prime minus 4. So I got a minus 4 of them, 1 of them. Okay, so that term goes away. This term goes away. 4 times 8 is 32. That term goes away. 4 minus 4.5, that's 1. That term goes away. 4 times 32 is 128 minus. That guy goes away. That guy goes away. This guy goes away. This guy goes away. Why is this 4 there? Why is that 4 there? Well, I think I have the problem right. I just can't figure out why this 4 is here. So, anyway, that's what the process you're going to have to do to get through those things. And with that, we're going to call 3-1 an end.